So I'm going to be talking about the water quantity component of this project, in particular, the effect of thinning on the snowpack and melt volumes. Okay. So there's a couple of different ways in which we could assess this problem. Historically, per watershed experiments has been one of them. As you can see in that figure, you could have two separate basins or hill slope if you wanted, and perform a thinning experiment on that one and compare it to the other one as a control site. Now, the problem with this approach is that it's typically very expensive to carry out. It's limited in the spatial conditions that you can do it, and the temporal condition, and thus it's hard to extrapolate to other regions. Now, the other approach that we can take, or that people has taken in the past, is using modeling, snow modeling experiments. Now, typically this has been done using relatively coarse snow models, so in the order of hundreds of meters to kilometers. And the main problem with this is that you cannot really resolve tree scale features, interactions between gaps and forest edge and openings and things like that. And this is really important, research has shown, because you need to resolve these small scale compensating effects, such as solar shading or the sublimation from snowfall being intercepted by the canopy, wind sheltering effects, etc. As you can see in this plot, in this figure. Now, in the last few years, there's been a new generation of snow models that are taking advantage of the new lidar data sets that are being available in order to configure very high resolution models, and I'll show you a little bit more about that later on the talk, in order to capture these small scale interactions between trees and the snowpack. So just an overall message of what previous studies have found, and this is a study from 2010 that is taking several, if not all of the studies in both North America and Europe, showing the effect of removing forest on the snowpack, on peak snow accumulation on the left, and the rate at which that snow ablates in the right. So you can see that, for example, here, there is, as you decrease your forest cover, you're typically getting more snow. And as you have more forest cover, you get less snow. Now, I want to highlight the big variability or the big scatter in each of these, in these plots. So for example, if you have 60% more forest, then you can go from reducing 60% in your snow accumulation to 0, or even increasing a little bit. So there is a lot of regional, climatic, topographic, and forest structure patterns that are really important, that basically gives you this sort of variability. So basically the message is that we need better tools to transfer these kind of results across region with different climate, topography, and forest structure. Now, like I was saying, in the last few years, there's been significant advances in how we can simulate these small scale processes in forest catchments. And here is one example from Broxton 2015 using a model called snowpalm, which is the same that I'm using for this study. And he uses lidar-based forest structure basically to define, how big the trees are, what's the density of those trees, and how those are scattered through the landscape. And you can see very interesting spatial patterns. So on the left, you have the observed from lidar as well, snow depth, and you can see these forest edges features that you can see from the lidar, and how that changes across the domain. And then the model does a reasonably good job capturing those, for example, forest edges features, as well as those in the open. So, and this is really important, again, because we need to capture this compensatory effect between increasing snowpack sublimation from having more solar exposure, and also decreasing canopy sublimation from reducing forests. So like the main questions that I'm going to address today is what physical mechanism control changes to a snowpack, both in accumulation and melt? What thinning scenarios provide the largest impact? What forest stands benefit the most from thinning? And if we can develop a decision support tool to try to predict and extrapolate changes to the snowpack. So I'm going to try to go quickly through these. Our study domain is the West Shore, of course. But now we're not doing all over the West Shore just because computationally this is very expensive to do. So we're doing 1 meter resolution modeling. So it takes a long time to compute and requires a lot of storage. So we're gonna focus on 2 watersheds, on Blackwood and Ward Creek, 2 main watersheds of the West Shore. And basically because they provide a pretty large spatial heterogeneity in terms of topography, climate, and forest structure. And also because we have snow tail stations that are going to provide us with estimate for snow water equivalent, snow depth, air temperature, etc., which we're going to need for our snow model experiment. So the model that I'm going to be using is called the Snow Physics and LiDAR Mapping, SNOPalm. As you can see in this plot, it can represent all those small interactions that I was talking before. So wind redistribution of snowfall, solar shading from the trees, interception and unloading of the snow from the canopy. It also includes a full snow and energy mass balance, as you can see right here. And it requires a LiDAR data set to basically capture the structure of the forest. So there's been some previous studies showing validation of this model, as I showed in the previous slide. But we also performed some site-specific validation in the Rubicon Mountain, as well as in Ward Creek, that I'm not going to show today. So we take advantage of this airborne LiDAR that was flown over the Lake Tahoe Basin in 2010, again, to represent terrain elevation, vegetation height, and vegetation density. And we use these to parameterize our model at 1 meter scale. And we also use hourly weather forcing bias corrected with local observation. So precipitation, air temperature, incoming short and long wave, wind speed, and relative humidity. And we do so in 3 weather years because we want to have a representative climate. So we do it on a normal year, relatively wet year, and relatively dry year. This is kind of the main workflow. We run the model SNOPalm using existing forest structure. And this is just an example for a small domain. We then do something that we call a virtual thinning experiment. So we take all the trees that are below 10 meters and all the trees that are below 20 meters, and we thin them virtually on the computer and rerun the model and compare that to a control run using the existing vegetation. We then upscale these results up to 30-meter forest patches. So it can be, they give you a better idea of what happens at those kind of scales, because 1 meter scales is not a really useful scale to work with. And from that, we develop a decision support tool to transfer these results. So let's look a little bit into a 1 meter scales results for the 20-meter thinning scenario. And you can see on red how canopy sublimation decreases as you decrease vegetation. So there is a very consistent decrease in canopy sublimation up to about 400 millimeters per year on average. Then you can also see changes in things like snowpack sublimation and net daily incoming radiation. And you can see how it changes in places that are relatively open and places that are like forest gaps, and what happens like on the forest edges like these ones. You know, all those kind of interactions are very important to capture the overall pattern. And then you can go ahead and look at changes into melt volumes and peak sweep, which is what we're after today. So we have these two relatively large watersheds. And so we define it a spatial classification that we call snow zones, and it's basically an elevation classification plus an aspect classification. So we go from low to high elevation into 5 different classes, and then from north to south facing aspects. So we have 10 different snow zones. As you can see, for example, if we look at things like peak sweep, the higher you go, the higher the peak sweep is, and things like that, like snow depletion date and so forth. You can see different differences between the aspect as well. So if we aggregate all the 1 meter results into this snow zone scale, and we look at normalized changes to each of the key mass fluxes. So we're talking about melt volume, canopy sublimation, snowpack sublimation, peak sweep, and the rain that goes through the canopy. This is what we can find, what we found. We normalize these changes by changes in leaf area index. So this has units of millimeters per meter square per meter squared. You can see that overall main changes come from a strong decrease in canopy sublimation in orange that is somewhat consistent throughout the domain. You can also see that there is a annual variability. So the dry year has a much different behavior in terms of normalized changes than the normal and the wet year. And you can also see, if we look, for example, melt volume, which is typically what we care most about, is that overall there is this trend that the higher you go, somewhat the lower this normalized change is. So we can see that there's some topographic controls, but there's some weather dependency as well. We can also look at normalized energy budget, and this is really important for the snow modeling piece of the analysis. So we can see that overall there is a compensating effect between increasing incoming solar radiation and decreasing incoming long wave radiation. So as we remove trees, we're more exposed to the sun, so we increase solar radiation, but also these warm trees emit a lot of long wave radiation that melts the snow, but as we remove those trees, we don't get that long wave radiation anymore. And this is particularly true at south facing aspects that get more solar heating. Now, if we come back into this 30-meter forest stand scale, and we plot these, such as in the y-axis, we have the existing forest structure mean leaf area index, and then the mean vegetation height for each of those 30 meters forest stands. And we color each dot by the increase, in this case, of peak sweep. We can see that there's forest patches with characteristics that increase your peak sweep the most. In particular, you can see in these very yellow colors that forest patches that are roughly between 5 to 15 meters and above 3 units of LAA on average are the ones that produce the most benefit into peak snow accumulation. And this is for the lower 2 snow zone. Then we look at the upper 2 snow zones. We can see that, you know, that's almost the same case, but then there is all the things happening too. For example, in the high north, there are things like wind redistribution of snowpack of snow that are also very important. Now, if we take a step back into these results and we compare it with the figure I showed you earlier, in which is putting these numbers in the context of what other studies have shown, we can see that overall these results agree with those shown by previous studies. But again, there is a lot of variability both at forest patch scale and also by each water year that you're looking at. So there is this need for looking specifically at those characteristics. It's really hard to drive like one just big, you could imagine like a big linear regression through all these dots, and that's not really gonna tell you, it's not really gonna give you a very good answer. So we go ahead and we try to develop this decision support tool, which is based on a random forest type of machine learning. And we use several predictors, so topography, elevation, aspect, slopes, etc., existing forest structure, and change in LAA. And we try to come up with a total change in melt volume and peak SWE as well, but I'm showing just melt volume here. You can see on this plot that LAA index is the one that produces the largest, is the variable most important in this analysis, as you could imagine. And we go ahead and do a little bit of a sensitivity analysis to see what kind of response we get from this decision support tool. And we can see that if we remove, for example, 2.4 meter square of LAA, we have these preferential zones, as shown earlier too, that south-facing aspect in somewhat lower to mid elevations are the ones that give us the most benefit. So we can use these tools to try to answer other questions, such as where should we target thinning in other watersheds nearby these two watersheds? What's the expected impact on the snowpack? And also look at watershed scale sensitivities to thinning. So I'm running out of time. So the next steps are going to be, so we did this at the west shore of Lake Tahoe. So we're going to include 4 different sites. The east shore, which has a much different climate. Sachem Creek, which is north of Truckee. Some area in the headwaters of the Yuba River, and then French Meadow more on the western slope of the Sierra. So the idea of including all these new sites is that we're going to have a much larger climate, forest, and topographic variability that's likely going to improve the fidelity of our estimates. And just quickly to conclude, our results show that thinning can significantly increase the snow accumulation, which has benefits for reducing wildfire risk and increasing melt volumes. We show that targeting relatively dense 5 to 15 meter tall forest patches located at low to mid elevation increases melt volume the most. This science-based decision support tool can be easily implemented. You don't need to run SnowPalm again. It's just a relatively simple machine learning tool that runs really fast, and you can apply that to neighboring watersheds. We're going to try to include more sites, which is also going to increase the transferability of this decision support tool to other regions. And also just point out that future studies should try to include feedback between the snowpack and tree regrowth to quantify the long-term effect of thinning, which were not included in this current configuration. And just the reference for you all, I'm happy to hand them out for you if you need them, and thank you.